Hello everyone. In this video, I'm going to talk about some basic characteristics of light, and we are going to apply them to study electrons characteristics in quantum model. First, I'm going to remind you in the quantum model of atoms, we are going to focus on electrons behavior. First thing we just need to remember, if we have like this interval between A and B, these 2 points, electrons cannot travel straight like this one. So we don't accept this pattern for traveling of electrons. If we have like this A and B, electrons can be travel this interval like this pattern. This pattern we call that like wave pattern, like ocean wave. So I'm sure you remember that one, ocean wave. In other videos I already talked about that. So we are going to have this assumption or conventions in quantum models. We call electrons as subatomic particles, but they are going to have some basic and fundamental properties of wave. When we have like this new definition for electrons, we call electrons in this model photons. So photons are electrons, but technically they have some extra or additional properties or like wave properties. In case we are going to study photons, it depends on our study. If particle parts of photon, it helps us to have better understanding of photons behavior. We assume that photons are particles. If wave properties of photons fit with our research or study, we assume that photons have mostly wave properties. So we call that dual properties, wave particle-like properties. One thing I may ask you to pay attention for waves like electromagnetic radiations or light, we just need to remember some basic characteristics. These basic characteristics are wavelength, and I'm gonna denote the wavelength by lambda. This is one of the Greek alphabet, lambda, so wavelength. And another one, I'm gonna talk about that. This is the nu is frequency. So I'm gonna write how to pronounce them. And another one is c, speed of light. So we are going to talk about the speed of light here and relate this information to each other. So for our class, we are going to focus on wave, and we are going to learn some characteristics of learn some characteristics of wave, like wavelength, frequency, and speed of light. So by this quick review, I'm gonna remind you, photons, they travel, electrons, they travel like a wave form, wave pattern. If I'm gonna draw a wave pattern like this, assume that we have like this, lambda basically defined as the distance between two identical points. The distance between two identical points. Identical points. We are going to know what does that mean, the distance between two identical points. Look at this wave I already reported as one sample here. Each wave has this max and mean. So let me write max and mean, or you may say peak, crest, or trough, or easily you can say positive, negative. So each wave has two parts, positive, negative, peak, crest, or trough, max or min. Which one is easier for you to understand? So I'm gonna say the distance between two identical points, Assume that we are going to talk about only two crests or only two trough. It's up to our study. You are going to say this is a crest, so another crest is here. The distance between these two, I'm gonna call that lambda. I'm gonna call it lambda. So you may say I'm gonna pick this trough and this trough. So you're gonna call that one lambda. Both are same. It's up to you. You may pick two mean or two max for your lambda determination. Whenever we say distance, it means we are going to work on length. So that is why we call that wavelength. Since this wavelength is going to be too short, we usually use nanometer to report the wavelength, or we are going to use the other small units to report the lambda. So the lambda, they are in general in order of nanometer. So this is the distance between the two crests, two troughs, or in general two identical points here in the wave. Another one is frequency. Assume that we have like this. For frequency, or let me write that one here, or nu, we have like this basic definition. Frequency is the number of cycles passed throughout a point in 1 second. 1 second. We are going to know what does that mean. Assume that we have this point here, and I'm gonna measure time 1 second and see how many cycles pass through this point. When we say cycle, we are going to talk about like this. We assume that this wave has one cycle wave. So I'm going to count it here. This is the one cycle, and we are going to assume that, for example, this is a 2 cycle. So we may say frequency for this one is 2 cycles per second, per 1 second. Unit for frequency is going to be like this one. I'm going to write the units for frequency. Frequency can be reported by cycles per second. So you may say nu is 2 cycles per second. Sometimes we say only per second. So we may say only per seconds. So you don't need to say cycles, because when you say 2, it means you can easily imply that 2 cycles per second, and we may report cycles by S1 negative. So you may say 2 S1 negative. It means 2 per second. But when scientists work on the frequency concept, and sometimes and most commonly used unit for the frequency is hertz, and we call the unit for frequency hertz. So we may say 2 hertz. It means 2 cycles pass through 1 point in 1 second. So 2 hertz means 2 cycles. 1 cycle means 1 hertz. So it depends on the number of cycles passed through each point. Right now, I'm gonna give it you this relationship between lambda and frequency, lambda and nu. Please look at these two examples. This is the first wave pattern, and this is the second one. I did my best to have a better drawing here. For the first one, if I'm going to measure the wavelength, for example, I'm going to measure like this. And if I'm going to measure here I'm gonna have like this one. As you see here, we have longer wavelength, and here we have shorter wavelength. Just comparing, just look at these two, you can easily compare. For wave pattern, for first one, longer wavelength, and for the second one, we have shorter wavelength. If we are going to measure the frequency, so if you are going to count the frequency for this one, it's going to be 1 and it's going to be 2. So we are going to have, for example, 2 as frequency. Let me write 2 cycles or 2 hertz. How about the second one? Here we have 1, here is 2, and right now we have 3. So nu is 3. So I'm gonna write this information here. For the first one, we have lower frequency, and for this one we have higher frequency. So as you see here, how you may find relationship between lambda and frequency. Longer wavelengths make lower frequency, shorter wavelengths make higher frequency. It looks lambda and wavelengths are behaving opposite of each other, and we say lambda is inversely proportional to frequency. Inversely. So easy to memorize that. So I'm sure that you can easily memorize like this one. Longer, lower. So means you can easily get that one. The higher frequency means shorter wavelength as well. So opposite of each other. Right now, I'm gonna give you another information than working on the equations. If we are going to work on the frequency, in chemistry, we are going to work on energy level of the in the atoms, working on the shells, and you will see what other videos in this series. So we prefer to change frequency to energy. Energy and frequency are related to each other. If we have like this wave A, so we call that low energy wave. So lower energy wave. And for this one, we call that higher energy wave. So frequency or and energy are interchangeable terms. We can easily use them for our concepts. There is difference between them. We need to know the equation, but I'm gonna say that if we have energy, you can apply that one, the behavior of frequency for that. Lower energy means lower frequency, and higher frequency means higher energy. So they are something you may consider for your memorization. Energy, it looks like frequency. So we have like this behavior for energy. So I'm gonna summarize it here. Longer wavelength make lower frequency, or you may say lower energy. Energy and frequency, they are directly proportional to each other. So directly proportional each other. But frequency and wavelength, as you see here, they have opposite behavior. They are inversely proportional to each other. Right now, I'm gonna work on the equation. So first, relationship between energy and frequency. So same behavior, same behavior. If energy increases, it means frequency increases and vice versa. The equation we have is E equal h nu. E is equal h nu. E means energy of photon. So let me write here energy of photon. Nu is frequency. How about h? So let me talk about h a bit later. So energy, the unit we use for energy is joule. So unit for energy is joule. Frequency is per second. Per second. So we are going to work on SI unit. I cannot use hertz. I need to know the SI units for frequency. So H is going to be a constant. We call that Planck constants. Planck's constant. And you don't need to be worried regarding this constant always given to you. I'm going to write H here. 6.626 times 10 to negative 34, and unit for H must be joule times second, because we are going to cancel out second to keep the joule. Right now, this is the equation you need to memorize for this section and apply that one. So for most examples, we supply this information for our students. So sometimes you don't need to memorize that. But as long as I say you memorize, it means you can easily save your time to solve your problems. But no worries, you are given this information for your exam. So I'm going to work on one problem here. Question says calculate energy of photons in 3.61 times 10 to positive 19 per second in frequency of 3.6119 per second. So question says calculate energy in joules of photons with this amount of frequency. So I'm going to write nu 3.61 times 10 to negative positive 19 per second. So I need to plug in the equation. E is equal h nu. So I'm going to plug it here. 6.626 times 10 to negative 34. And let me write the unit for this one by another color. Joule times second multiplied by 3.61 times 10 to positive 19, and unit is per second. As you see here, first let me work on the units. Second and per second cancel out. So the only unit remains here is joule. So you need to calculate and report your answer by proper suffix. So 6.26 times 3.61, I'm gonna get that one 2.39 times negative 34 plus 20, I'm gonna get 10 to negative 14. So it looks this is the answer for this example. Please double check to make sure you have the correct answer here. So this is the final answer for this one. It looks the amount of energy is too small when we have photons, and it's totally makes sense. Amount of energy must be too small because electrons or photons can carry a small amount of energy. Let me work on another equation. We are going to work on frequency and wavelength. So I'm going to remind you, if frequency increases, wavelength decreases. So it would be similar to the previous slide. I'm going to write one equation. It's going to have the similar pattern. C is equal lambda times nu. C is a speed of light. So this number is a constant, So is equal to 2.998 times 10 to negative 8 meter per second. So some textbook call that 3.00. So we may consider like this one. So sorry, let me erase that one. So I don't know why I write negative. So let me write it here. 2.998 times 10 to positive 8 meter per second. Right now, I'm going to plug in the equation. So always 2.998 times 10 to positive 8 meter per second is equal lambda times nu. So this is the equation. You need to know how to work with that one. So always we have two questions regarding this. You may have either lambda or nu, and you need to calculate another one. So let me ask you to calculate like this one. What is the frequency in per second of photons at 3.81 nanometer at lambda is equal 3.81 nanometer? I'm going to solve this problem. Question says, what is the frequency? So frequency, I'm going to write that one, new question mark per second. If we have photons at this wavelength, 3.81 nanometer. So I'm going to write the equation. In the equation, C is lambda nu, and we are going to calculate only for frequency. So I need to divide both sides by lambda. Lambda and lambda cancel out. So nu is C over lambda. So I'm going to write it here. C, the number constant given to you, no worries, always is given to you 8 meter per second over lambda. Guys, lambda reported by nanometer. So I'm gonna write 3.81, and the meaning of nano is 10 to negative 9 meter. So you just need to convert word version of this SI prefix nano to 10 to negative 9. So I'm gonna write it here. 3.81 times 10 to negative 9 and meter. Meter and meter cancel out. So the only thing remains here is per second, or you may write S1 negative. So you just need to calculate this one. Let me calculate that, and I do ask you, please calculate by yourself to make sure you can get the number like me. So it's going to give us like this number, 7.87, because we are going to report by 3 suffix. The number reported here, it has 3 suffix. So 7.87 times 10 to positive 16 per second. So this is like the calculation I did have for you guys. So please remember, for all of the calculation, we need to apply the suffix based on the original number that we have. So finally, I'm gonna review these two equations here. Energy is related to frequency by this equation, h nu, and h is 6.626 times 10 to negative 34 joule second, and C is, let me write, lambda nu, and C is 2.998 10 to positive 8 meter per second. One question, can we combine these two? Absolutely you can. So if we have this question as first question and this is a second one, from the second one I'm gonna write nu based on this C over lambda. So we have C over lambda based on the equation number 2. So I'm gonna plug in the first equation H nu. So I'm gonna write H, and nu has this definition C over lambda. So I'm gonna write C over lambda. So I'm gonna derive this new equation H C over lambda. So this is a new equation. H and C, they are the constant. So as you see here, we have this constant, and you can easily plug in here lambda and solve the energy. So let me give it you one example here. Calculate amount of energy in joules of photons at lambda 2.50 nanometer. So let me change this number. I'm gonna work on it a little bit better one, 410 nanometer. So I'm gonna work on this. Calculate amount of energy. So question says energy in joules. So I need to derive the one equation for energy in joules when we have this number 410 nanometer. So I'm gonna write that one. Lambda is 410 nanometer. So you may use 2 times. You may use the equation first, convert the lambda to the frequency, then plug the frequency here and solve for E, or you can easily plug in this equation. E is hc over the lambda. I'm gonna write that one here. H is 6.626 times 10 to negative 34. Let me write the unit by another color. I'm gonna make sure you visually you can learn everything based on the unit cancellation, and this one is meter per second divided by, again, 410. It means we can write 410 times 10 to negative 9 nanometer. So I'm going to write 410 times 10 to negative 9, and unit is nanometer. So I'm going to work, sorry, why did I write nanometer? We already canceled, we already converted to meter. So look here, if you have nano, you just need to write 10 to negative 9 and 10 meter. So like I did. So right now, look, second and per second cancel out, meter and meter cancel out. The only unit it remains is joule. And I need to report my final answer. Absolutely, you know that by 2 suffix, because 410 it has 2 suffix. So you just need to calculate and report it by 2 suffix. And I may ask you, please calculate and check your answer with my answer. And let me report my answer here. 4.8 times 10 to negative 19 joules. As you see here, again, we have two small amount of joules or energy here. So to finalize this video, I wanted to show you what is the meaning of wavelength frequency, and their equation. So for this video, I wanted to make sure you learn how to solve the problems by these two equations, and if we are going to combine them, how to derive this equation and work on this. Thank you for watching this short video.